So gas evolving reactions. If we look at this reaction here, we've got potassium sulfide and sulfuric acid. And they can do an ion exchange, the same pattern where they're going to swap partners. But what happens with these guys is they actually make a gas instead of water and salt or just two different ionic compounds. So this is an example that forms a gas directly. There are some other reactions that form gases more indirectly. What happens with sodium hydrogen carbonate, which is baking soda, and hydrochloric acid, we get this ion swap and we end up with sodium chloride. And what would the name of this one be? It's an acid, right? It starts with H. So you cover up the H, and CO3 is carbonate. So this is carbonic acid. Carbonic acid is unstable. And that's just something you have to remember. Carbonic acid is unstable, and it decomposes into water and carbon dioxide. And this is what makes the fizz in carbonated beverages. They're carbonated. They use carbonic acid to make the carbon dioxide. Now when you drink it, you're not drinking carbonic acid. That sounds scary, doesn't it? But that's where the carbon dioxide originally comes from. So here's an example. You can see it better up here. So if we pour, what are we pouring in here? A solution of sodium hydrogen carbonate into hydrochloric acid, we see fizzing occur. The ions, what am I looking at here? So here's the, okay, these are the reactants. Sorry, just trying to get my bearings here. Here's the sodium hydrogen carbonate and the hydrochloric acid. And they're going to swap partners, but then that's going to decompose into carbon dioxide. I'm sorry, I'm really lost this morning. Carbon dioxide and sodium chloride. And this carbon dioxide is a gas at room temperature, and so that's what gives rise to these little bubbles. Okay, that was probably a waste of time talking about that slide. Decompose means to come apart into simpler substances. That's what chemists mean when they say decompose.
But it's not the same as ionizing.
It is not the same as ionizing. That's a good question. Let's go back to this equation. So here we have this one substance forming two substances. It's not really reacting with anything. It's just falling apart. And it's not ionizing because these are not ions. Okay, very good question. This book doesn't really talk about the different types of reactions yet, but this is an example of what we call a decomposition reaction, where you have one thing coming apart into smaller substances. It's a little bit like, you bury a dead animal and it decomposes, right? Well, what does that mean? It means that it breaks down into simpler substances. Good question. So we need to recognize the types of products that are going to result in gas being evolved. And thankfully, there's just these four types. The first one is when you have a sulfide reactant. That was the first example I showed you today. If you do your ion swapping and you end up with H2S, you need to recognize that that is a gas at room temperature and specify it as such. You just have to remember that. There's not really any reasoning about it. It's a memorization deal. That's hydrogen sulfide gas. It smells like rotten eggs. It smells really bad. These other three are a little different. You do the ion swapping. Some books call that a double replacement or a double displacement reaction. And you're going to end up, if you end up with one of these as a product, carbonic acid, sulfurous acid, or ammonium hydroxide, you need to remember that these three substances are not stable. They will decompose. Thankfully, there's a bit of a pattern in what they decompose into. They decompose by losing a water molecule. And so that can help you remember what gas they produce. So let's write that out down here. If we end up with a product of H2SO3, you have to remember that that's going to decompose. And how it's going to decompose is it's going to lose a water molecule. So that's what you memorize. The rest of that, you can figure it out by looking at this. So, oh, well, all of these guys decompose by losing a water molecule, so if I get rid of the H2 and I get rid of one of the O's, I am left with SO2. And that is the gas that's given off. That's sulfur dioxide, and that also doesn't have a good smell. A lot of sulfur compounds smell bad. Ammonium hydroxide. My 4s have not been good lately. Ammonium hydroxide will also generate a gas by losing a water molecule. What's left when we take two H's and an O from this formula? NH3. What's the name of that compound? Ammonia. And that is a gas at room temperature. And the carbonic acid we already saw, but I'll put it down here just for completeness. That will decompose. Water will come off, and what's left is CO2 gas. So you're like, great, more stuff to memorize. But there's kind of a pattern in here. So if you get one of these products, if you get H2S, know that that's a gas. If you get one of these, recognize that they will decompose by losing water, and what's left after you remove two H's and an O from these formulas are these gases. Okay? Any questions about that? Yes?
So, like, how would that look in a reaction if we did a reaction equation and we ended up with like H2CO3?
Mm-hmm.
We end up with that, but you would expect us to write water and the gas.
And CO2, yes. I think we have an example. Yeah, I think this example will illustrate how do we actually do that. So here we have limestone, which is calcium carbonate. Limestone is insoluble in water, but dissolves when a hydrochloric acid solution is added. Write the molecular and net ionic equations for this reaction. So calcium carbonate, what's the formula? CaCO3. So what we've done in our heads is we say calcium, it's in group 2, it's got a +2 charge. Carbonate is CO3. 2 minus, we've got a +2, -2, we need one of each, and we write that down. That's the thought process that goes on there. So calcium carbonate, what's the state of limestone? It's a solid. And then hydrochloric acid has the formula what? HCl, and that will be aqueous. So predicting the products, we are going to swap the ions. So we've got calcium, and we've got carbonate, and we've got hydrogen, and we've got chloride. And we're going to swap partners. So we're going to end up with calcium chloride. Is that going, now remember we put a liquid onto this rock. So there's water present, so we're going to ask ourselves, is calcium chloride soluble or insoluble? It's soluble. Chlorides are soluble except for silver, mercury 1, and lead 2. This is not an exception, this is aqueous. The other combination is these guys. So not thinking ahead, just, kind of following patterns, we're going to end up with, gosh, I didn't do a very good job of saving some space. We're going to end up with H2CO3 just by putting the ions together. And that's when the little flag should go up in your head. Oh, that's one of those. Okay? So what you can do there is you can either write it all out, or you can say, oh, that's unstable, that's going to fall apart and form water and carbon dioxide gas. So I'm going to erase this and write what it forms. That forms water, which is a liquid, and carbon dioxide gas. Does that answer your question? Yeah. So you do the ion exchanging, the swapping partners, and if you get one of those 4 compounds, then you have to recognize I have another step. With the hydrogen sulfide, you just write gas and you're done. But with the bottom 3, you have to take that intermediate product and write what it decomposes into. So here we have our equation. Are we done with this equation? No, it's not balanced, is it? So we're going to look at this. We've got 1 calcium and 1 calcium. There's 2 chlorines here, so I'm going to have to put a 2 over there. I've got 1 carbon and 1 carbon. I've got 2 hydrogens and 2 hydrogens. And then 2 plus 1 is 3 oxygens and 3 oxygens over there. Okay? I'm going to erase this. That's our molecular equation. Now we need to write a net ionic equation. So we learned how to do this yesterday. So are we going to split this calcium carbonate into ions? No, because it's a solid. So we'll just copy that guy down. Calcium carbonate, solid. Are we going to split this into ions? Yes, because it's a strong acid, right? It's one of the 6 strong acids. So then I'm going to write plus 2 H pluses, those are aqueous, and 2 chlorides, and those are aqueous. I'm using the 2 because I've got 2 of these units. And if I take this unit apart, then I've got 2 of each of the parts. Always have to include charges on ions when you're writing these net ionic equations. And so those are the reactants. And then let's look at the products. Should I divide calcium chloride into ions? Yes, this is an ionic compound and it's soluble. So I'll write, I've got calcium 2 plus, aqueous, and I've got 2 chlorides, and I get that 2 from this formula. In this unit, I have 1 calcium and 2 chlorides. So when I pull it apart, I get 1 calcium and 2 chlorides. How about water, liquid? That stays intact. And how about CO2 gas? That also stays intact. So H2O, liquid, and CO2 gas. Is that a net ionic equation? No. What kind is it? It's a complete ionic equation. It's showing all the ions. And usually, at least mentally, we have to go through that step before we can get to the net ionic. So now what we need to do is get rid of the spectators. Is there anybody that's the same on both sides? Just the chloride, right? So what I'm going to do is I'm just going to go erase him. Because I don't have room to write all this over again. So I got rid of the chloride there, and I got rid of the chloride here. So it looks a little weird, but it's correct. So the net ionic equation here is calcium carbonate plus hydrogen ions gives us calcium ions and water and carbon dioxide. What this tells us is that the Cl doesn't matter. It's the H, the hydrogen ions, that matter. So if we added a different kind of acid, it would also react. The chloride had nothing to do with it. It had to be there because you cannot have a solution of just positive ions or negative ions. You cannot separate them that way. You just can't. Any questions?